Howdy y'all, I'm Joe Hughes and I'm here to give a presentation entitled From VMs to Kubernetes. This is going to be introductory concepts and some basic live deployments. There's a bit.ly link here on the screen at the bottom for the sample code that we will demo in this session. There will also be some pointers included at the link for getting your first Kubernetes cluster up and running to play along. So again, howdy. In case you missed it before, I'm Joe Hughes. I'm here because I'm a VMUG leader and I just love to get people engaged and learning. You can find me on Twitter, I'm at jhughes, or you can find me at fullstackgeek.net because nobody will ever spell my last name properly. Again, bit.ly link here at the bottom to help you get a Kubernetes cluster built and then the code to follow along with the demos. So let's get straight into this. Why learn Kubernetes? I found this quote a couple years ago when I was first getting into Kubernetes and playing around with it, and I thought it was absolutely fantastic, especially when we're talking about the differences between VMs and Kubernetes. The quote is, "It's like landing on Pluto when people are still trying to figure out Mars or other tools properly." Or to quote one of my favorite songs by one of my favorite bands, don't aim for the moon when you're shooting for Mars, right? My big consideration with a lot of this is just for you to understand fundamental differences that come with this, right? You kind of have to forget some of the things that we know about traditional vSphere infrastructure to really do this properly. Kubernetes is a platform that's all around orchestration, and it has amazing power and benefits for you based on the platform managing things for you. So rather than writing code or a bunch of health checks or dealing with things manually that are not relevant to the applications we're actually trying to get running, a lot of that goes away and it's not yours to worry about or maintain anymore. But there are some fundamental things that are really important for us to understand as we're getting into Kubernetes, especially for vSphere admins and a lot of the things we just bring along with us. But first, let's level set some expectations right now. Again, this is going to be basic concepts of containers and Kubernetes and seeing some basic demos in a Kubernetes lab environment. Hopefully, you will start to understand the basics of a lot of these components and how they work together, as well as some important differences from virtual machines, and then we can get comfortable with starting out with Kubernetes. And will this session make anybody an expert? Absolutely not, but it should help you to learn some of these terms, kind of see how things coordinate and interact with each other, get the basics and some of these things actually in action. And I hope it will be helpful as the first or at least another step in your learning journey. So Kubernetes or K8s, what is K8s? The 8 here just represents the 8 letters between K and S in Kubernetes. So Kubernetes or K8s or K8s are all one and the same. Kubernetes is the Greek word for pilot or helmsman of a ship. This is a project that was spun out of Google as an open source orchestration platform. Think about managing containers and workloads and doing that at Google scale. That's where this came from originally. It started as the Borg platform internally, but then they open sourced it, made it available to everybody, and there have been just tens of thousands of other contributors, lots of engineering effort that have all been made into the platform through open source contributions. The current versions of Kubernetes and the state that it's in is just because of the number of people that have been running these in labs and productions and scaling out workloads and then contributing back to the platform itself because it is open source. Kubernetes is designed to be loosely coupled collection of components that are all centered around deploying and maintaining and scaling workloads, right? This loosely coupled concept means that all of these components have very little knowledge of each other than the control mechanisms, and they function independently, which makes them easy to replace or integrate with other systems or, even swap in additional components that have some more native functionality for wherever it is you're actually trying to run these things. But Kubernetes is also built with this concept of having a declarative state for describing our environment and then having control loops that'll make it happen. And we'll see this a little bit more when we get into some of the terminology and everything, but let's take a step back and really understand how our environments are changing. Since the main purpose of Kubernetes is to manage and orchestrate container-based workloads, let's first describe what a container is. And a container honestly could be considered a very special operating system process because it's essentially a specific application running in an operating system. But we also want to discuss some basics and benefits of containers themselves. Containers have reduced resource requirements, essentially no operating system per application, and they are application focused, not operating system focused like virtual machines are. And all of this is due to being able to leverage C groups and namespaces on a host that allows for limiting and isolating host resources. A C group controls what a process can do, and a namespace controls what a process sees. Essentially, when a container is run, right, these two operating system features are used to provide allocation of resources to the application and isolate it from other containers running on the same underlying OS that these live on. Namespace basically means that this process is given its own CPU and memory resources. It's allowed to see certain portions of the host network stack or the host file system up. Right. And then the control groups control resources at the container level, right? So that C group is managing resources container level down. Namespace restricts what resources are going back up to the host. But since the container is essentially a process running inside of an operating system, it still requires an operating system to run, but we no longer need an operating system per application or per workload. This makes containers very lightweight and portable while allowing for some specific and very granular control to resources rather than traditional operating system processes. So let's discuss this a little bit more with a visual. So we want to get into a quick visualization of VMs versus containers with regards to running applications. With VMs that we've dealt with before, we start with our infrastructure, which means all of our hosts, our network, our storage. Then we have the hypervisor to manage on top of that. For each VM, we're going to have a guest operating system. Then we have any required binaries or libraries needed for the applications. And then finally, the actual application that sits on top of this. We're going to have this for each one of these instances that runs, right? And for every instance of a virtual machine, we're probably going to have all of this still built on golden templates that are built by deploying a base operating system and keeping it patched and updated. Then once you've instantiated an actual VM out of this base template, each one of these VMs now becomes an operation to manage, the lifecycle for this independent operating system, no matter what base it was built from. Plus, we've also got to deal with all of these binaries and libraries and any security updates or patching, and then application patches that go on top of all of this. And if you ran into an instance where you needed different binaries or libraries, right? This was even us having to manage different directories, different symbolic links, or specifically have individual VMs every time we had to stamp out someplace that we couldn't deal with these different dependencies or different versions, right? If we just needed a specific binary or library for a specific application version, sometimes we had to have side-by-side virtual machines just to deal with these interdependencies that couldn't live together. Now let's move over to the container space. We start again with the same infrastructure, meaning all of our hosts, our network, our storage. Now we have an operating system rather than a hypervisor. And finally, we have another process that lives on top of this, which is our container runtime engine. In this instance, we're talking about containerd. So containers decouple applications from the underlying host infrastructure. That makes it easier to deploy these on different OS environments or even different clouds. Kubernetes supports multiple runtime, container runtimes, containerd, CRIO, any other implementation of the container CRI. You may have also heard of Docker, which was a very popular container runtime interface. And then the kubelet, we'll explain this in a little bit, but it's an agent that lives on our worker nodes, and the underlying container runtime interface with these host C groups and everything enforce all of the resource management for all of our pods, all of our containers, and all of our CPU and memory requests and limitations for all of these things. But to get back to the comparison of VMs to containers, a container contains an image, right, which is the application and also all of the binaries and libraries that you need to run that application itself. These containers are image-based, which means that they are a ready-to-run software package because it contains everything we actually need to run this application. The image is made up of a binary that has all of our code, any runtime that's required for this application, the application itself, any system libraries, any default values that need to be passed in for settings. But then each container that you run is repeatable. Since it has the dependencies included, you get the same behavior wherever you run it. To us, in the end, these containers are really going to look like a process running on an host operating system. And then the container runtime is going to be the software that's responsible for actually running these containers. We don't have to interact with it other than saying, go run these. But these images are defined in such a way that they're built with a base image, right? Think a very lightweight OS. Any additional files they need or any commands that need to be run, inclusion of any of the binaries, libraries, and then the actual application, that's the workload that you're wanting to deal with. These fully compartmentalized container images are what it is that we're actually dealing with maintaining and deploying around. So let's quickly cover some core concepts of Kubernetes itself. So by design, a container is meant to be immutable, right? You would not change the code of a container that's already running to make modifications to it. If you already have a containerized application and you want to make changes, then you would need to build a new image that includes the change. That's going to add another layer to our image itself, and then you're going to recreate the container itself from that new updated image. So gone are the days of remoting to a server and just making live changes on a server, with the notable exceptions of things like a very high impact production down scenario. Kubernetes is also built with the concepts of a declarative state for describing our environment and then having control loops to make that happen. We describe our environment and then Kubernetes works to make that the current state. And as we're moving away from the days of old monolithic applications where an entire guest OS had to be updated and patched along with all the binaries, libraries, and the applications themselves, we eliminate much of the pain of application health. With Kubernetes, a lot of these components, they should be built to be self-healing, right? If they're not responsive, then we should be able to put in another instance of an application and it shouldn't cause us problems. All these components are meant to be loosely coupled to make a useful application, but each of the components themselves should be capable of independent updates. And as we work on refactoring our applications into these smaller purpose-built components, it becomes easier for us to write or just consume shared reusable libraries and tools, and also to publish these back for open source use by the rest of the community. Now, refactoring many monolithic applications will just not happen, or it can take months or years to develop to put this all together and test it and ship it. But however, this entire new design model for applications and deployments makes this much more feasible than in the past. So, what a cluster. First, I just love this image that actually comes straight out of the Kubernetes documentation for the components of a Kubernetes cluster. When you deploy Kubernetes, you get a cluster, even if it's a cluster of one. With this blue line that we have here on the left, we see a dividing line between the control plane and our worker nodes. The control plane manages the worker nodes and the pods in the cluster, and these master nodes should exclusively run the control plane and not user applications. In production environments, you want the control plane to run across multiple computers, right? Multiple hosts even, not just nodes. And a cluster will typically contain multiple nodes, providing like fault tolerance and high availability. In smaller or lab environments, obviously, single nodes are going to be fine for getting started. And we want to take a look at all of the control plane components that are also listed on the right side, but we have 5 that we really need to understand, right? There is the Kube API server, etcd, Kube scheduler, control manager, and then the cloud control manager. That really only comes into play for cloud-specific control logic. But these control plane components make global decisions about the cluster, right? Like where we're going to schedule workloads, as well as detecting and responding to events in the cluster, whether that's somebody starting up a new pod or when the replica count for a deployment is no longer met and actions need to happen. So let's dig into these one by one. Quickly, we've got the Kube API server, right? This API server is a component of the control plane that exposes the actual Kubernetes API, which is how you interact with Kubernetes itself. This is the front end of the Kubernetes control plane. It's designed to scale horizontally. That means it scales by deploying more instances, and you can have several instances of the API server and then just balance the traffic across those instances. Number 2 is etcd. This is going to be a consistent and highly available key value store, like a database, used as Kubernetes' backing storage for all of the cluster data. If your Kubernetes cluster uses etcd for the backing store, make sure that you have a backup plan for this data, getting it outside of Kubernetes. The Kube scheduler, right? This is the control plane component that watches for newly created pods that don't have a node assigned to them, and it selects a node for them to run on. But it takes a lot of factors for scheduling decisions. The Kube control manager. This is the control plane component that runs controller processes. Essentially in Kubernetes, controllers are control loops, right? These watch the state of our cluster and then make or request changes when they're needed. Every controller tries to move the current cluster state closer to the desired state. A controller tracks at least one Kubernetes resource type. These objects have a specification that describes the desired state. The controller for that resource is responsible for making the current state come closer to that desired state. Finally, the last one to mention here is the cloud controller manager, right? This is the control plane component that embeds cloud-specific control logic, and it's only going to run controllers that are specific for your cloud provider. So typically not something we're going to have to worry about as we're getting started inside of a vSphere or a lab environment. But one last point about desired versus current state, right? Kubernetes has a cloud native view, and it's able to handle constant change. So your cluster can be changing at any point as work happens, and control loops will automatically fix failures. This means that potentially our cluster never actually reaches a stable state. As long as the controllers for the cluster are running and are able to make useful changes, it doesn't matter if the overall state is stable or not. Now, as we get onto the application sides of things for worker nodes, we've got a Kubernetes cluster that's made up of worker machines called nodes that actually run our containerized applications, and every cluster has at least one worker node. These worker nodes host the actual pods that are the components of the application workload itself. And there's a couple of components that exist on every node. So we want to understand the kubelet, which is the agent that's actually running on each node in the cluster that makes sure that containers are running inside of a pod. It takes all of our specs that are provided and ensures that the containers described in there are running and healthy. This also does not manage any containers that have been run on side of our nodes that were not created by Kubernetes itself, right? It leaves those alone. Then there's also the kube proxy. This is a network proxy that runs on each node in the cluster. implements part of our service discoverability concept, right? This maintains all of our network rules on the nodes, and then these network rules allow for communications to the pods from network sessions either inside or outside of your cluster. And then the underlying component we're going to have for all of this, obviously, is that container runtime that exists inside of here. And again, this is going to be at the host level and not necessarily something we're going to see inside of most of these descriptions, but again, required component for all of our nodes to have that container runtime interface. Lastly, we want to note some add-ons, right? These are going to use some specific Kubernetes resources to implement some cluster level features, right? And these are essentially going to be like a system namespace at the very top end to just always be running on the back end. Biggest one's going to be DNS. There's other add-ons that are not strictly required, but all Kubernetes clusters should have cluster DNS, as many things rely on this. This serves as the DNS records for just Kubernetes services. Any containers that are started by Kubernetes automatically include this DNS server in their DNS searches. To wrap up all of this stuff, right, there's some important things that we need to mention to show some differences between VMs and Kubernetes. Again, Kubernetes creates DNS records for services and pods, right? You can contact services with DNS names instead of IP addresses. And then every service that's in the cluster is assigned a DNS name, even the DNS server itself, right? So just a little bit of a distinction of DNS and Kubernetes before DNS inside of the rest of your network. And then lastly, storage and volumes. On-disk files in a container are ephemeral, right? They're not going to persist beyond the life cycle of a container itself. This can present some problems for applications when you're running them in containers, especially if you plan to use that same data for a different version of your container after an update or an upgrade. One problem with all of this is the loss of files when a container crashes, right? The kubelet will restart the container, but it starts with a clean state. It will not have that data on disk anymore. Second problem is going to occur when you're sharing files between containers running together in a pod. But there is a concept of a Kubernetes volume that solves both of these problems. Kubernetes supports a bunch of different types of volumes, and a pod can use any number of volumes simultaneously for different types, right? There's going to be ephemeral volume types that have just the lifetime of the pod itself, or persistent volumes that extend beyond the lifetime of a pod. Think of this as external storage. When a pod ceases to exist, Kubernetes destroys those ephemeral volumes, but it does not destroy permanent volumes. Be sure that you are aware of what you are defining, and by default, it will be defined as an ephemeral volume, so you want to make this distinction to not lose your data. But then, for any kind of volume in a given pod, right, the data is preserved across container restarts. And at its core, a volume is really just a directory, possibly with some data in it, that's accessible to all the containers in a pod. How that directory gets created, the underlying storage, all of the contents, is all determined by the particular volume type that you use. There's multiple types that you can use, but you can, consider using traditional underlying storage, such as vSphere data stores, fiber channel backed volumes, iSCSI, NFS, local paths. If you're in the cloud, AWS, Azure, GCE storage of different types. You can even use empty paths for things like a scratch space, right? And then we also have this concept of a definition of a storage class, which is a way that administrators can describe the class of storage that you're offering. Different classes might map to different quality of service levels or to backup policies, or different policies that are determined by your cluster admins. Pods, labels, deployment services, oh my. So a quick point to anybody coming from working with containers outside of Kubernetes, right? Are we talking about containers here? No, we're actually talking about pods when we get into Kubernetes. We'll cover this when we get into the code, but the smallest workload that you're going to be managing within Kubernetes itself is actually going to be a pod, and it's one or more container images with a little bit of wrapper around it. Then labels are going to be something that are actually important. They're a core part of the workload management, unlike vSphere tags, which would be the closest reference inside of vCenter. These are going to be associations that we actually have where a particular pod is labeled as part of a deployment, gets labeled as a part of a particular project and things like that. These labels can be carried across different levels of components inside of Kubernetes so that you can easily identify and figure out what it is we're talking about with tagging something, and essentially that label is used everywhere. Deployments are actually the what and how of things running inside of Kubernetes. It's the image that we're trying to run, how many of these we're trying to have, what it's supposed to look like, what services it's supposed to tie into, and so on. And then finally, services themselves. These are an abstraction to expose an application running on a set of pods as a network service. Kubernetes will give pods their own IP addresses and a single DNS name for a set of pods, so you can load balance across them. But you want to have these attached to services for exposure outside of your cluster and make it a little bit easier for these to be understood or consumed outside of Kubernetes. And then lastly, we're going to take one last look at cluster architecture before we dive into demos. Up here at the top, we have our Kubernetes master node that's handling our control plane instances. At the bottom, we actually have nodes where the applications are going to run. So inside of Kubernetes, we're going to have scheduling, which refers to making sure the pods are matched to nodes so the kubelet that lives on that Kubernetes node can actually run this. So a scheduler is going to watch for any newly created pods that don't have a node assigned. It's going to then be responsible for figuring out what's the best node to put that on. Looking at the nodes themselves, right? These can be, again, a virtual or physical machine, depending on your cluster. Every node is managed by that control plane, and it contains all the services that are necessary to run pods on these nodes themselves. Again, typically you'll have several in a cluster, but if we're talking about learning or resource-limited environments and labs, right, you're fine to have just a single node. Again, these are going to run the kubelet, the kube proxy, and a container runtime. In this instance, looking at the actual workloads that we've got here, we've got a pod. Pods are essentially just a simple wrapper for a container, but every pod in a cluster gets its own, unique cluster-wide IP address. And pods can communicate with all other pods on any other node without NAT, and they can also communicate with any of the other agents that are on the node itself. But when we look at these pods, we see here that these each have a label, right? This little tag-looking icon that's here. Some of these actually have a service, which are going to be the colored dotted lines here, between like this node on the left and node on the right. We actually have this red label going up to this service at the top of the screen here. So this is a service that's distributed with multiple pods running on multiple nodes. If we hit that service endpoint, right, that DNS name, or even specifically that IP address, we're essentially going to load balance, and we're going to hit any running instance of that pod on whichever node it's on. Kubernetes is just going to balance that for you. So you're going to hit, either instance. When we look at the pod that's on the node on the left here that has a blue labeled service, that's only a single instance of a pod, but it still has a service associated with it. So it can be exposed, even if it's just that single instance that's running inside of your Kubernetes cluster, it can be exposed outside of it. I know that some of these are very fuzzy concepts at this point, but basically you're going to have a pod. It's going to have labels that'll make it easy for you to identify when you want to work with this thing and more of them. Then if you want to deploy it elsewhere, you're going to give it a service. You could even make it accessible to a load balancer and things like this. So pods basically are containers with a little wrapper. Labels are how you identify things. Service is going to be how you're going to expose these outside of the Kubernetes cluster. And with all these basics covered, let's jump into the demos. Howdy y'all, and we are back for the demos. So let's go ahead and get into this real quick. So I've already got this running up in Docker. So if I fire up my local host, we can see that I've got this running on port 49,000 with just this simple web page with a message for hello from the September Global Virtual Event. So we have this running in Docker, which is great, but we want to actually get this running inside of Kubernetes. But I just wanted to give everybody just a quick view of what it is that we actually have inside of this web application so we can see what everything looks like. So now what we've got here inside of Kubernetes, we want to just take a look and see what we're working with here. Okay, so I'm going to go ahead and run kubectl config get context. So as you can see, I'm actually just running this on my desktop. This is a Windows 11 box running Windows subsystem for Linux, and it's got the Docker desktop installed on it. So it's actually the Kubernetes instance inside of Docker just for a very simple deployment of everything to get into this demo environment here. If we take a look at our nodes, we will see that I've got a single node that's in here, just the control plane role running on it, right? So lab environment, single node, which is running as the master and running as the worker. Not ideal for production environments, but totally fine for a lab, and especially for copy and paste code that we're doing here just to try and get things running. And if I run kubectl get pods, we can see that there are actually no resources found in this namespace. So the first thing we're going to do is actually get our first pod up and running. So I've got this spec that's here in this YAML file on the left, and it's showing that it's a kind of a pod, right? So for metadata, we're naming it vmug-first-pod. We're applying a label of project vmug demo. We're giving the container a name of vmug-container. Giving a container port of 8080. I've got some resource limitations for it, and I'm just tagging which specific image for this web app that we're actually going to be running. So inside of this, I want to go ahead and deploy my pod. So we're going to run a kubectl apply -f for the pod YAML file. Now if I run my kubectl get pods again, we will see that we have the first pod running. So congrats, we're now running our first containerized workload on Kubernetes. And if I run kubectl describe pod vmug-first-pod, we've got some information that comes back here, right? It's a lot of information here on the screen, but essentially we can see we've got the name of vmug-first-pod. It's the default namespace. It's got a priority. It has our label of project vmug demo. No other annotations. The status is running. It gives us an IP address. It shows us the ID of the container, this one being an individual single container inside of this pod. But the containers that are involved in it, right? What's the state for the ports and all of these things? What's the limit for resources that we've given it? What are the conditions as far as the statuses for everything? And then the actual events that ran to create this, right? So we have a description of this pod. And if I come back in here and go take a look at this again, hold on a second. We had... what was our get pods? So we have this thing up and running. So we should be able to hit port 8080 on my local host, and I should be able to get to this pod. Oh, but it's not actually working. Well, that's because of the fact that we don't actually have this thing exposed currently. So what we're going to do to get this working is go ahead and put a service in front of it. So let me clear my screen, and what I want to do at this point is go ahead and run this config file for a service-vmug-local. So we're defining the kind of a service, right? I'm giving it a metadata name of service-vmug-local. I'm telling it to apply a node port 8080, which is going to get passed down to the target on the container itself, and the port I'm exposing on the node is going to be 32,000. And the selector that I have is this label for that project vmug demo. So let's go ahead and apply this file. So kubectl apply-f for that service vmug demo. Let's get our services and take a look at what we've got here. So we now have the service for svc vmug local, which is a node port that's applying port 32,000 to pass it down to the container port of 8080. So now if I do this, I can go to port 32,000 on this particular node, again, my local host, and I can get back to port 8080 on the container itself because I'm passing a node port down to the container. So let's go ahead and get rid of the node port because we don't really want to present things that way. And let's assume that we're going to be using a load balancer as if we were actually in a public cloud. So for this deployment file here, I'm defining the kind is a service. I'm giving it a name of cloud-lb. I'm defining the type for this one to be load balancer instead of node port. And I'm telling it the port that I want to present locally is 80. The target port is 8080, which is what's getting passed down to my container. So now we'll go apply this other load balancer service, kubectl apply-f svc cloud.yaml. We'll go get our services again. And this time we can see we've changed from svc vmug local, which was a node port, to this cloud lb, which is a load balancer. The external IP, if you were using a load balancer that actually had a true production network, it would give you the external IP address as well as the ports that are getting exposed on this. For this one, since I have just straight localhost, what I can do is actually just delete the port, and I can expose this to where port 80 on my local host is actually getting passed down to 8080 within the container itself. I'm sorry. 3363 is what's actually getting sent here and then getting translated by the load balancer to the target port on the container itself. So let's go ahead and clean everything up for the next quick demo. We're going to delete our service and delete our pods. So those are going away, and we will go ahead and jump into the next demo, which is going to be a deployment. So the first thing we want to do once this comes back is we want to actually go ahead and get our pods just to show that our environment is clean. And we're going to start covering what's in this deployment YAML file. So here we're defining the type as a deployment, or the kind as a deployment. We're giving it a name of vmug-deploy. Inside of the spec, I'm telling it I want 5 replicas. So for this pod, I want 5 replicas for that project of vmug-demo. Right, that's the template we're leveraging inside of this. The container's name is going to be vmug-cntnr, passing it the same container ports, giving it the same resource limits, and tagging the same image that I want to do. So we have no pods, we have no deployments currently, and I want to go ahead and do a kubectl apply for this deployment.yaml file. So the deployment is created. We're going to look at our deployments, and we can see that it's already deploying these. If I run a get pods again, we will see that I probably already have all 5 of these running, right? If I go back and look at my Git deployments, we can see that we've got 5 out of 5 up to date and available. The next thing we want to take a look at is the self-healing that exists within Kubernetes. So I'm going to force this a little bit because I'm actually going to go through and delete a pod. So we're going to do a kubectl delete pod. Let's pick this third one here of SL4KM. So if I delete this pod and then run kubectl get pods yet again, we should see that we'll have one that's terminating, and by the time this returns and shows us, we're already going to have one that's going to be up and running in its place. As soon as the control loops detect that there was a pod that was in a not healthy state, right, where I forcefully terminated it, it's going to say that this doesn't match the state of the deployment where we wanted 5 replicas, and it's going to automatically fire up a new pod to get this up and running and get it back to our desired state that's in the configuration. So at this point, we're just waiting for kubectl get pods to come back to show us, and there we go. We no longer have this SL4KM, and we have a new pod in its place, this Q9SXX. So if we go back and look at our deployment again, we have 5 out of 5 that are defined. So we are back to our desired state. All right, so for the next quick demo, we're going to cover scaling. So what we're going to do is we're going to actually update our deployment file here. I've deleted the deployment out of my environment, but we're going to change the replicas from 5 to 8. We're going to save the file, and we're going to go ahead and apply that deploy.yaml file. So kubectl apply deploy.yaml. We're going to get our deployment and take a look at it, and we're spinning up 2 out of 8 so far. So if you take a look at our pods, we'll see them coming up pretty quickly. So we've got all 8 up and running. So now what we want to do is take a look at manual scaling. So for this, what I'm going to do is I'm actually going to run this kubectl scale command. So I'm going to define that the replicas is 6. So earlier, we created the deployment because we applied a file, right? And if we go through and modify this, we will see a similar thing. If I go put this up to, say, 9 or something, we're going to see that we have applied this deployment. Whereas here, when I ran kubectl scale, this shows me that I've scaled the deployment, right? Because I ran this interactively. It was not deploying from a file. It was not applying a configuration file. So if I go look at my pods again, we should see that these are terminating to get us down to the new definition of this replicas 6. Now, the thing that we've got to be careful of is when we go look at our deployment itself, right? The deployment has been modified on the command line to show that we are at 6 deployments for the desired state currently. But what we have inside of our configuration file here is still the original 8. Right, so we have an instance where the running state no longer matches the desired state that should be defined in source control. So just a thing to be aware of, you can go modify things interactively on the command line, but if you're mixing back and forth from doing live configuration and modifications on the fly versus configurations via files, configuration files, then you're going to end up in an instance where you are running things that don't match from one to the other. So now if we update the deployment back to 8, we modify this again, we can go reapply our file, right? And we can now see again deployment configured rather than deployment scaled. If we go look at our pods, we should see that we are getting back up to 8 pods that are running. And if we go look at our deployment again, we are back to the original 8 that were defined in the config file itself rather than modifications at the command line. All right, so for the last demo that we've got here, we're going to run really quickly through a rolling update. So what we're going to do here is we're going to update our deployment YAML file with some additional details so that we can actually define how it is we're going to do a rolling update of this. So let me get my spacing in here correctly. And what we're defining is this new section here. So we're defining the number of seconds that are going to be the minimum before we're determining whether or not the pod is ready or not. We're determining the strategy type of rolling update. And then for the rolling update itself, we're defining 2 different parameters, a max unavailable and then a max surge. These can be integers or these can be percentages, but what we're defining here with max unavailable 0 means only bring new containers online before we're taking old ones off, pods. And then for the max surge, this is allowing us to define the number of additional pods beyond the defined spec for this replica that can be brought up. So we're saying 1. So essentially we can bring 1 new one on and then delete 1 old one. The last thing I'm going to do here is update my image to vmug app 2.0.1, and we're going to go ahead and apply our new deployment file. So now we can go check out the rollout. So we're going to run kubectl rollout status deployment vmug-deploy. So we're waiting for this rollout to finish, right? And as of this point, basically it's saying 1 out of 5 replicas has been updated. So the first one's been updated. Now number 2 is going. And once all these get updated properly, with this new image that's in here being rolled in one at a time, we're going to see that there's actually a change to our web application itself. So we've got 3 out of 5, 4 out of 5 will be next, 5 out of 5 will be after that, and I'm running a quick kubectl apply for my service cloud for defining that local load balancer so that when I just do a refresh of localhost, we'll see the web app change from the old version to the new. So we've got 4 out of 5 replicas that have been updated. We're just waiting for this last one to update, and we will take a look at our web app. And if I refresh the page here, what we've got now is the goodbye from the September Global Virtual Event. Hopefully you guys enjoyed these quick demos just for some very, very basics on a simple Kubernetes lab environment to see some of the power that really comes in with Kubernetes and things that we can do with working with these containerized applications. All right, thanks y'all. Okay, so just a quick thanks for everybody for coming out. I hope you guys enjoyed the content. I hope you guys enjoy everything that we've got today in the September virtual event. There are, again, resources for all of this if you go to the link here for bit.ly to find all the sample code and some quick run-throughs to try and get you up and running on a Kubernetes cluster to play along with all of this. If anybody has any additional questions, again, you can find me on Twitter at jhughes or joe@fullstackgeek.net. All right, thank you all for coming out. I hope everybody has a good one and learned a little bit today. Thank you, guys.